Hello, stats friends, we're back. This is a 2-day lesson, just FYI. It's still in the data analysis chapter, and today we're going to do section 1.3, which is describing quantitative data with numbers. So we've been looking at quantitative data, which remember the data itself is numbers and not categorical, but now we're going to be describing them with other statistics. And some of them you've seen, and some of them might be brand new to you. So here goes nothing. So we have learning targets, of course. All right, the first item, I'm hoping this is a bit familiar to you from your work in previous math classes, but we're going to talk about how we can measure the center. We had been using the median earlier in like our dot plots and whatnot, because the median was pretty easy for us to find without the use of any sort of arithmetic. But now let's talk about another measure of central tendency, which is the mean. So remember, mean is synonymous with average when you were in little kid grades. So the mean of a distribution of quantitative data is the average of all the individual data values. So same thing as average. To find the mean, add them all up and divide by how many observations you have. So of course, because it's math and it's upper level math, they're going to give some crazy notation to you in a minute. And it looks like this. So add them all up and divide by how many you have is this notation here. This is the fancier notation on the side where it says this is called a sigma. It's a capital Greek letter sigma. And it says to sum all of your x values and then divide by how many you have. So it's the same average and mean formula you've known for years. So here we have some data on the number of goals scored in 20 games played by the 2016 US women's soccer team. So to find the mean, and in class we should stop the, well, not stop the video, we should stop and do this. But we're going to start by adding them all up and then dividing by 20 because that's how many data values we had. Now, one thing to caution you about, and I know it's been a long summer, um, don't forget that if you are going to do this all in one step on your calculator, you're going to need to put parentheses around that numerator, or you can hit enter before you divide by 20. You can't just say /20 at the end because you got that horizontal script in your calculator. So make sure you can calculate the average or the mean to be 3.15 goals. And you'll notice if they kind of compare that to what's on the dot plot, the mean, and okay, so I didn't do the median here, but let's see, I probably could, right? 10, 11-ish. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 2. The median is 2, which is not the same as the mean, okay? So we're going to talk later about how some of these statistics are resistant and some aren't, and how they can affect the data can affect the measure of central tendency. So X bar, by the way, is what they use for the mean of the sample. Anytime you see X bar, they're referring to a sample of data. If you ever see this funny little guy, this is a mu, spelled MU. In English, it is a Greek lowercase mu. It refers to the mean of the population. So notation is super important in stats because if we write X bar and we really meant mu, it makes a difference. So another set of vocab here is if we're referring to characteristics of the sample, then we are looking at what's called statistics, which you might notice is a major name of the course, a piece of the name of the course. So if it's about the population, that is called a parameter. And parameters, typically we can't calculate those. It's just not feasible. So you'll notice a lot of our job as statisticians is to use sample statistics to make conjectures or inferences about the population's parameter. That's the idea. So here's the mean number of goals scored in 2016 by the US soccer team. But what if we exclude those last 2 games where we might have had possible outliers? So it was a little hard to tell on this dot plot back. Oh, no, it's not. Not hard at all, Abruzzo. Just got to open your eyes. Yeah, I'm kind of thinking those are outliers, guys. So we'll talk in a moment about how we know if they're outliers or not. But for now, let's just go with our hunch that says, oh, back. Let's say they are outliers. So if we exclude those 2 games, that means we only work with the first 18 pieces of data from that list once it's in order. And then we find that our mean is 2.44, which is a lot closer to that median value, which still is going to be 2 in this data set. So you'll notice that mean got pulled to the right because of the skewed right distribution and because we had those outliers out on the right. So if a statistical measure is resistant, if it isn't sensitive to extreme values. So the median is what we call a resistant statistic, and the mean is non-resistant. So the mean is sensitive to extreme values. The mean is not a resistant measure. That's the clear hint there. So I kind of spilled the beans here. The median, the midpoint of the distribution, the number such that about half the observations are smaller and about half are larger. So remember, we've seen cases where the median isn't exactly like a single value, so we have to like average the two in the middle. But either way, it's an about measurement anyways. So to find the median, arrange them from smallest to largest. And this idea we've kind of been tinkering with. It says if n, the number n of data values is odd, then the median is directly in the middle of the ordered list. So what I do, like if I have a really big list of data and I have an odd number of things, like if I had 123 things, what I know is if I add one number to that, 124, and then I cut it in half, whatever that number is, so in that case 62, 62nd thing in the list is my median, okay? So that only works for if it's odd. If the number of data values is even, then the median is technically the average of the two middle ones. So what I do, again, it's just what I do. You don't have to do it this way. If it's an even number, so let's say 120, what did I just come up with? Well, whatever, I'll do a different one. Let's say it's 100. Okay, so if I take that value and cut it in half right away, I'm down to 50. I know that 50 and then the next one, those are the two middle values. So 50 and 51, the 50th and 51st value are the middle ones. So once I found them in my list, I would average them together to figure out the actual median. I have good news for you. In a moment, we're going to talk about the calculator and how you never have to hand calculate these things ever again, probably. Woo! All right, so we have some new data here. We have highway fuel economy ratings for a sample of 25 model year 2018 Toyota 4Runner. Oh, hello, Toyota 4Runners tested by the EPA. All right, so here's our raw data. It was very difficult to look at. So then what did they do is they sorted it. They put it in a kind of a list from least to greatest. Again, still hard to read. And then remember, we had 25, which is odd. So if you use the Abruzzo method, if you add 1 to that, 26, and then cut it in half, so 13, the 13th thing in the list was the median. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, boom, 13. Yeah, I know, spoiler alert, it was bolded. But so 22.4 is the median in that sorted data. Back when you're a little kid, you did that cute thing where you like crossed off the beginning, the end, beginning, the end, beginning, the end. And that still works. But, you know, once in a while, you'll get this gigantic data list and you're like, oh my goodness, I don't want to do that. So here is a list. Oh, back to soccer. So the same 20 games. Now, we already found this answer, but that's okay. We know that the median was 2. Now, in this case, because it was 20 games and it was even, this is the 10th, right? And Abruzzo's method is take that one plus the next one and average them. Well, if I average 2 and 2, it's still a 2. So, spoiler alert from a few minutes ago, the median is 2. I think they're going to compare that in a minute. Yeah, they are. All right, so remember when we took the outliers, oh, never mind, wrong data. So in the fuel economy example, the median was 22.4 and the mean was also 22.4. So that kind of tells me that the mean equaling the median means we have some, well, roughly symmetric data, let's put it that way, with no outliers, or at least not a single outlier in one direction. It is kind of interesting to note that there was what kind of might be called an outlier, but there's kind of an equally weird outlier over here, so they kind of cancel each other out. So you'll see that the mean and the median are very close in that data set. Now, if you look at, I don't even know what data this is. Some other random data, probably in your book, I should go look at it. We have some data that is definitely not symmetric and is definitely skewed to the left. So what you'll notice is the median is here at 19, but the mean got pulled to the left. So remember we said the mean was non-resistant, which meant it could get pulled by any sort of skewedness or outliers. That did not happen in the fuel economy problem because we are so symmetric. All right, so what happens if we have a skewed right data set? This is about the soccer goals, and remember we had those two outliers to the right, which skewed our data to the right. So that pulled the mean away from the median because remember the mean is non-resistant. So there you go. Now, do remember when we took those outliers out, it was the mean came back closer to the median. So that was an important note. All right, the effect of skewness and outliers on measures of central tendency center. If a distribution of quantitative data is roughly symmetric and has no outliers, the mean and median will be the same. Okay, so if you have symmetric data, no outliers, but we did see that one case where there appeared to be outliers, but they were like canceling each other out, we still call that symmetric. So the mean and median were the same. If the distribution is strongly skewed, the mean will be pulled in the direction of the skewedness, but the median will not because the median is resistant. So for a right skewed distribution, we expect the mean to be greater than the median. For a left skewed distribution, we expect the mean to be less than the median. So I really am a visual learner. So these questions pop up on the multiple choice portion of the AP stats test, and they use inequality notation. So they'll be like mean less than median, blah, blah, blah. Uh, I know I'm a math teacher. It should be easy for me to figure out, but I always kind of sketch it out because it's just easier for me to figure out. And we'll do that together in class as well. The median is resistant to outliers, but the mean is not. So this is again another vocab word. Unfortunately, it's a vocab term that's misused a lot by students. So the range is the distance from the minimum to the maximum. Now it is essentially an absolute value, but if you just think of it as max minus min every time, you'll be good. The problem is a lot of people say, oh, the range is from 13 to 22. That's not what they mean by range. Range is a single value. It's the difference from the maximum to the minimum. So we got to be careful about that. So that soccer problem again. When remember we had them lined up at one point, but the smallest was 1 and the largest was 10. So the range, don't say from 1 to 10, the range is 9 goals. There's a difference of 9 goals from the largest to smallest. And there's that caution word. It is not the range is a single number. The range is not resistant to variability. Is not a resistant measure of variability. So what that means is if you were to have outliers, that would affect your range, which is a measure of variability for us today. If you got rid of the outliers, it changes obviously the measure. All right, this one is probably new to most of you, standard deviation. Now, standard meaning typical. Deviation means difference or distance in this case. So it's the typical distance of the values in distribution from the mean. This is kind of hard to understand. In class, we're going to go through some hand-done examples of how we calculate standard deviation so we can kind of go through it better. But here's the idea of how we could calculate standard deviation and variance because they kind of go hand in hand. I will tell you there's very few moments in life where you're going to have to hand calculate the standard deviation, but it's still important for us to understand where it comes from. So let me back up and say, if you end up taking a stats or a psychology stats or some sort of applied stats class, in college, they really like you to calculate these by hand. I'm just going to warn you. I don't know. I don't know why. I'm not in charge. I don't know why. All right, so first step, calculate the mean of the distribution. We can do that. Now we're going to calculate the deviation. So the deviation is where you take each value and you see how far away it is from the mean, but it has to be in that order, okay? Value minus mean. Now in a minute we'll see why we do this, but next thing we do is we square each of the deviations, and then we're going to add them all up, all those deviations that are squared that we just found, and we're going to divide that sum by n minus 1. We'll talk more in class about why n minus 1, but for now just go with it. What we just calculated in steps 1 through 4 is called the sample variance. But the variance, because we squared it, it has the wrong label. So like in the soccer goals question, the label would be, I'm making this number up by the way, 5.8 goals squared. Well, we're not interested in goals squared, we're interested in goals. So the last thing we'd have to do to find the sample standard deviation is to take the square root. Don't you love math? Like, of course I would do that. All right, so here's that weird notation where they have like value minus mean. Remember, we're going to square each one of these, then we're going to add them all up, and we're going to divide it by n minus 1. We'll talk in great detail in class about that because I know you have questions. And then we're going to square root that value so we have the right label. So here's an example of it. And this is actually pretty easy and nice to do in the tables of your calculator. We can also do it by hand. We have a pretty short data set, so I wouldn't mind doing this one by hand. So finding the mean, dunzos, it's a 3. Now this is 11 high school students who were asked how many close friends they have, and here's their responses. So the mean is 3. So now we're going to calculate the deviation. So we're going to take each one of these answers and we're going to subtract it from the mean, subtract the mean from it. So 1 minus 3, 2 minus 3, and so on and so on and so on. And you'll notice some of the values are positive and some of the values are negative. So now, this is something they didn't talk about in this slide, but I would kind of like to. If I were to add up all of these deviations, they would add up to 0. And this is an interesting conversation to have with students in the room. Obviously, I don't have any right now, but the reason is because we were calculating off of the mean, some of the data values will be a little above and some of the data values will be a little below the mean, and some will be exactly equal to the mean, and it's all going to balance out. And therefore, when you add up this deviation column, you're going to get a 0. Well, I can't do a lot of math with a 0, guys, right? So to kind of fix that in math, they said, well, before I add them up, what if I squared each of them? So these negative values will become positives. And then obviously the 2 will square to a 4, 1 doesn't change, yada, yada. All right, so now when I add up the squares of the deviations, I get an 18, okay? So that's something I can work with. So our fourth step is to take that 18 and divide by n minus 1. So n minus 1 is a 10. Remember there was 11 things, so 1 less than that would be a 10. And our variance, we're calculating a variance right now, and they use that to notate variance, is 1.8. So if I use the labels from this problem, there's a variance, a sample variance of 1.8 friends squared. Well, I don't really care about friends squared. I don't even know what that is. So the final thing we do, take the sample variance and we square root it. So if you were to square root that equation, you now have what's called the sample standard deviation, and it comes out to 1.34 close friends, which is a lot easier to understand than close friends squared. So that's the sample standard deviation. What does that mean? All right, well, first of all, let's talk about properties of it. The sample standard deviation is always greater than or equal to 0. Okay, it has to be a positive value. The larger the values of sample standard deviation indicate greater variation. It is not a resistant measure of variability, and it measures variation about the mean. Okay, so if I kind of translate this third one here, outliers would affect your standard deviation. And if you got rid of the outliers, you'd get a new standard deviation. That might be more appropriate. Let's back up a moment because I really didn't have a slide in here where they talked about what this means. So the sample standard deviation is 1.34 close friends. That tells you how much it varies for every standard deviation you go out from the mean. So if I was trying to talk about this data, I would say the 11 high school students who were sampled, the average number of friends was 3 with a standard deviation of 1.34 close friends. So this is kind of opening the doors to some other topics in stats, but in the future, in the near future, we're going to talk about, okay, how many deviations can you go out and not be too far out? If you've already taken an AP Bio course, I think you know that the magic number is 2, right? 2 standard deviations out. And after that, you're getting scary. All right, we'll talk more in the future about that, I promise. All right, let's talk about another way to measure our data. We're going to talk now about measuring variability by the interquartile range. So quartiles would be if you took your distribution data and you broke it up into 4 groups that have roughly the same number in each quartile. So first thing you gotta do is arrange them from smallest to largest, and then you find the middle. And then after you find the middle, which is the median, right? Then you find the middle of the 2 halves that are left, okay? So the first quartile would be the median of the first set of data, so the ones that are to the left of the median. And then the third quartile would be the middle of the right side of the data. So it's hard to like visualize it, It really has to do with where the data is clustered, and this is a nice indication on the number line. I like the way they did that. So a couple more vocab words. The first data value is called our minimum, and then you see your Q1. You have your median and a Q3, and then the highest one here we call a maximum. So the interquartile range is another way for us to measure variability today, and it is the distance from Q3 to Q1, and again, it has to be in that order. So if you were to subtract value of Q3 minus Q1, you have what's called the interquartile range. What's cool about the interquartile range is it's a quick, easy way to calculate variability. I like it. It also, in between there, Q1 to Q3, that contains 50% of your data. So that's a pretty big chunk of your data if you're looking for some sort of an interval. So here we have travel times for 20 New Yorkers. I don't know what they're traveling to. I'm guessing their work. So the first thing they did was they sorted the data from least to greatest. And then now they're going to have to find the median. So remember, if it's 20, that's even. So halvesies would be 10, and because it's even, we got to go 10, 11. So 10, 11, you're going to have to average the 10th and 11th together, which is these guys here, boom, boom. So the median smack dab in the middle. And then if you were to find the center or the median of the left side and also the right side, you would get, this is interesting, 15 and 15, so that's 15. And then 40 and 45, which we would have to average. Okay, so there is our Q1. Here is our median when they average 20 and 25. And here's our Q3. Sometimes kids get confused how they landed on the 15 and 15. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data values, right? That are to the left of our median, because our median doesn't actually exist in the data set. It's this ghost figure right here. So 10 cut in half would be 5 and 6. So 1, 2, 3, 4, 5, 6. These are the two they had to average. I really hate when my data comes out to even ones. It always messes with my brain. Even numbers. Okay, so the next thing they do is they find the measure of variability for this problem, which is the interquartile range. So Q3 minus Q1 is, voila, 27.5 minutes. Make sure you label that, minutes. So this is how we interpret the interquartile range. The range of the middle half of travel times, or you can say the middle 50% of travel times for New Yorkers in the sample, that's important, is 27.5. So we kept referring to, ooh, I think they're outliers, or ooh, they might be outliers. There's actually a rule to determine if something is an outlier, and it's using the 1.5 rule. So if you take the interquartile range and you multiply it by 1.5, that's kind of the acceptable distance off of the median that you're allowed to be without being considered, off the Q1 and Q3. That's the acceptable distance that you're allowed to be considered in the bounds of the data. Now, this is very mathy. I appreciate their attempt. I just don't know that this is the easiest thing to look at. So when you have a data set, which in a minute we'll see them as box and whisker plots, you know you have an outlier down here in no man's land if you do Q1 minus 1.5 times interquartile range and your value falls below that number. Okay, so if you do this calculation here and you have this calculation come out to a 2.8, but you happen to have a 1.3 out here, well, you're going to have to toss that one out as an outlier. Now, similarly, for a higher end outlier, something up here in the number line, if you do Q3 plus 1.5 times interquartile range, so let's pretend I did that and I came up with 7.8. But I have a data value up here at 10.2. I'm going to have to cross that guy off. He's too high. He's an upper end outlier. Again, I don't think that inequality notation is really easy for kids to interpret, so we'll do some graphical displays a lot in class. So I think we're coming back to that EPA Toyota 4Runner question data that we had earlier. So this is the dot plot for all that data, and we've already calculated Q1, Q3, and interquartile range. Well, someone did. I mean, I didn't. but again, I promise I'll show you on technology how we can do this all. So the lower outliers would be anything that is smaller than Q1 minus 1.5 times the interquartile range. So if they do that calculation, that would be 22.2. The lower outlier would be less than Q1, 22.2, minus 1.5 times 0.04, and that came out to 21.6. So right here is 21.6. No, I can't count. This is 21.6. So if anybody is smaller than that, to the left of that, it's considered an outlier. So this guy right here would be considered an outlier. I wish I had children with me. I feel like I explained that bad. All right, so now let's talk about the upper end outliers. I'm thinking this one might be, but let's do the calculation to find out. So a higher end outlier would be anything bigger than Q3 plus 1.5 times interquartile range. So Q3 was 22.6 plus 1.5 times the interquartile range of 0.4. So after we do this calculation, we get 23.2. So 23.2 would be boom right there. So anything above that is considered an outlier. So this guy right here is an outlier. Now, notice how having that visual display really helped you understand, like, okay, here's my cutoff. Anything above it or below those were outliers. I really appreciate when people do that for me because I'm definitely a visual learner. So to kind of interpret what's going on here, the cars with fuel economy ratings of 21.5 mpg and 23.3 mpg would be considered outliers by the 1.5 times interquartile range rule. If this was an AP question where you had a free response, you would have to like literally name by the 1.5 times interquartile range rule. I don't necessarily know that they ask for calculations, but you got to show them. All right, why do we look for outliers? Well, they could be just inaccurate data values. Sometimes it's bad sampling or someone entered data poorly. It happens. They can indicate remarkable occurrences. So in that soccer goals, question, and we had some outliers at 9 and 10, maybe something happened in that game that we have to go back in the history books and realize, like, what was going on in those two games that they scored 9 and 10 goals? They have a lot of injuries on the other team. I don't know. They can heavily influence the values of some summary statistics. So remember how we talked about mean as being non-resistant? So the mean and the range and the standard deviation, basically they get screwed up by outliers. So we have to be careful. The 5-number summary of a distribution of quantitative data. Oh, by the way, I think this is the end. That previous slide was the end of the first day. So if you were just looking for the first day's lesson, maybe stop here. The first quartile, Q1, the median, the third quartile, Q3, maximum. Oh, and I skipped the minimum up there. So when I ask for the 5-number summary, that's what I'm looking for. Minimum, Q1, median, Q3, maximum. So we've already found all of those, and the min and max are, frankly, they're obvious. The minimum is the smallest and the max is the largest. So there's the 5-number summary. What this allows us to do now is create what's called a box plot. And a box plot is a visual representation of that 5-number summary. It doesn't necessarily align with the dots themselves. That's a little confusing to kids because they're hoping to see like all the dots from the dot plot. It's a different idea. So if we're trying to make a box plot, we find the 5-number summary first. So we did that. Now we have to identify if we had any outliers. And remember, we did this on a previous example. So we can kind of make some notations where the limits for the outliers would be from the Q1 and the Q3. So this mark here is the end of my data, and this mark here would be the end of my possible data. Then we're going to draw and label horizontal axes. Okay, so we already have that. There we go. Oh, outliers, sorry, I skipped a slide. All right, draw and label horizontal axes. What they mean by label would be the title itself of what you're measuring. And then don't forget you want to put some numbers down too, because we're going to scale the axes. Now, if I go back for a moment, that scale from the original problem is the same scale we're using here. They didn't change anything because of the outliers, and you'll see why in a minute. We're going to draw a box. Now, it's not just any box. The box itself is from Q1 to Q3. And sometimes you'll see box and whisker plots that are like up high in no man's land, and they shouldn't be on the axes because it's hard to read everything if it's on the axes. So 22.2 to 22.6 was the beginning and end of Q1 to Q3. Then you're going to draw a line where the median is. Now, don't be confused. It's not always directly in the middle of Q1 and Q3. I know it feels like it should be, but not always. And then we're going to draw the whiskers. Now, the whiskers only extend to the last data value that isn't an outlier. That's I got to be cautious about that, guys. Let's back up a minute. Go back to our little plot over here. So remember, this range here was like, okay, you can accept any values all the way out to here. Our whisker does not end here. Our whisker ends here, which is the last acceptable data value. And then same thing over here on the right whisker. It's going to end here at the last acceptable data value. Okay, skippy, here we go. There we go. So there's your whiskers. Now, one thing that you'll see me do, and your book does it as well, and your calculator will do it, I'm going to put little stars where there exists outliers because I don't want to forget them. They're notable, okay? They're just not, I'm not keeping them in my data set because I know they are outliers, but I don't want to forget them. So I put little stars or asterisks or something where those outliers occur. Box plots do not display each individual data value in the distribution. So that's a bummer about a box plot. If you're trying to figure out where those little tiny dots came from, a box plot won't do it for you. They don't show gaps or clusters or peaks. So it's not the best distribution, but it is a type of distribution that will help us kind of do a quick analysis of our data spread. Okay, now what you've been waiting for, the technology. So that was not super fun to do by hand. And I'll be honest, guys, if I'm forced to do one by hand, I'm also on the side doing it on my calculator because I always like to double check myself. You know my graphs aren't that pretty, so we got to double check. So first thing we're going to do on our calculator, and this is specifically for a TI-83 or 84, but similar calculators have similar entries. If you happen to have the Inspire, there is an appendix in the back of the book that tells you all the keystrokes that you need for the Inspire. And I am by no means an expert at those calculators, so we're going to have to reach for our resources if you need help with that. So enter your data into list 1. So if this was in class live, I would have you guys do this. I would like you to stop the video and do this as well. Enter the data of the pairs of shoes that a typical teenage boy owns into your list 1. Pause the video to do that. And then once you have that data entered, you go back and you go to a different menu, so Stat, and you slide over to where it says Calc. And you choose the option that says One Variable Stats. Now, if you have one of the newer operating systems, which our classroom calculators do, a dialog box will pop up and you have to tell it like where your list is. So it's in list 1. And then because we don't have a frequency list going on where like we have a tally count, just leave that empty. And then when you hit calculate, or you guys who have the older one, just hit enter, it's going to assume it's list 1. You should get this data here, a screen that looks like this. Now you'll notice there's an arrow here that indicates that if you scroll down, you'll see more and more and more. So the reason we want to be able to scroll down is because there's some other information here that I need to figure out. So the very first thing they pop out in 5-number summary, in the one variable stats is the mean, which is great to know, right? And then later on, they have S sub X, which is standard deviation. This is a different calculation. We'll talk about that later on, but this is the standard deviation. It tells me there's 20 things in my list, and then keep scrolling until you hit minimum. That's what I'm interested in. So the minimum, the Q1, the median, the Q3, and the max, those are the 5-number summary. So if they ask me for the 5-number summary, boom, there I have it. Minimum, Q1, median, Q3, max. This thing underneath here, this is someone using Minitab. It's a statistical software. So there is a good chance that on the AP exam, they're not really interested in are you able to type things on a calculator? They're interested in how you can interpret them. So they might give you this printout and you're supposed to take this printout basically and create something from there or interpret something from there. So, we do want to note, The TI-8384 gives the first and third quartiles of boys' shoes distribution as 6.5 and 11.5. Minitab says at 6.25 and 11.75. What happened? So here's why there's a difference. Minitab and other softwares use slightly different rules for locating quartiles. And this is why I get really irritated when they're odd, because some people, they don't include those ones that were counted, and some programs do include them, and it gets very confusing. So remember, as long as you're close, you're good, because the definition of quartiles was, about 25% of the data is here. Like, they're not looking for exact science here. That's the good news. As long as you can interpret what you have, that's important. So, what if I actually had to make a box plot? Now, with that 5-number summary that we have, we could easily create a box plot. And I say we, meaning you, because anything I create is going to look like a hot mess. So what if I wanted something that's a little prettier to look at? They are talking about tablets here. Now, I don't have tablets, so I'm not doing that. But we can still do this on the calculator. So we're going to go to this other data. So do me a favor. If you're using a TI-8384, great news, because that's what we would be using. I would want you to pause this video right now, and I want you to put the Apple data. What are we doing here? I should read the problem. I'm so dumb. Back up. I was like skimming and I was like, Apple, Samsung tablets. I don't have one of those. The data is Apple and Samsung tablets. I quit. Oh, it must be summer. Okay, so we want to enter the ratings for Apple tablets into list 1. I was wondering why I had these weird instructions of using tablets on my TI-83 lesson. Oh, dumb. Okay, sorry guys. And then I want you to put the data for Samsung in list 2. For now, just do that. So you're going to pause the video, enter this data into list 1 and this data into list 2. Just type carefully. Pause the video and then start up again. Okay, once you have the data put into list 1 and list 2, we're going to set up our statistics plots. Now, because we have 2 data that we're trying to compare, we're actually going to turn on plot 1 and plot 2. So if you go to the second y equals menu, which is the setup for your plots, right now, I have plot 1 turned on the screen because it's emphasized, it's darkened. I could do the same thing with plot 2 by hovering over it and hitting enter, and it'll toggle between on and off, okay? So for now, though, I want to set up one plot at a time. Plot 1, I'm going to choose. Now I got to be careful which kind I want. There's 2 different box and whisker plots. This one's called a modified box and whisker plot, and this is just the normal box and whisker plot. You actually want the modified one, and I'm going to choose it every single time because it will identify any outliers for you. So, why would I not want it to do that? So choose the modified one, and then you need to tell him, the calculator, where your data is at. So plot 1 is from list 1 for us. Frequency just means everything shows up one time, so keep it as a 1 always. You can choose whatever color and marker you want. And then you're going to do the same thing for plot 2. So go over to plot 2, turn it on, and then you want to choose modified, but this time for plot 2, you're going to want list 2. Okay, list 2. Now to get a picture like you see on my screenshot here, once you have all that set up, you need to hit zoom and then choose zoom stat. I believe that's zoom 9. And you're going to see this. So I wasn't paying careful attention. I think the blue one was my first list. So this is, which I already forgot what it was. Was it Apple? All right, so this is the Apple data, Apple tablets data. It appears to have 2 little outliers over here. So they modified it for me. That was nice. And then on the Samsung data, it's claiming there's no outliers. That's important to notice. Whoops, I didn't mean to hit that. So this is it creating the box and whisker plots for you. Now you'll notice if I hover over with the cursor by hitting the trace and just keep toggling, it'll go from point to point to point to point to point to point to point. So if the question was, please find the interquartile range, well, you could have done that a few different ways. Without actually doing a lot of calculation, you could have done the 5-number summaries in your calculator. I guess if you wanted a visual for it, you could have done it this way and then found Q1 and Q3 by hopping over them. I can see the median right now on the screenshot, but that's not the only thing it'll show me. So what we're going to have to do next is now take these box plots and actually compare them, and talk about, remember our favorite things, center, shape, outliers, variability. Okay, and we're going to use comparative words and also context of the problem. So I don't think they actually ask us to do this, but we should. I feel kind of bad about this. I should go back and read the problem. I'm really missing half this problem. All right, it's the rating for the different types of tablets. Overall ratings produced. Okay. Okay. Cool, cool. All right. So here's what I'm noticing. This is Apple, right? So it doesn't really matter what order we talk about these in, but if I talk about shape, um, a lot of people would claim that the shape of Apple is skewed left. You could comment that if you remove the outliers, it has a more symmetric distribution, but it's still kind of skewed left. You'll notice the left tail is much longer than the right, or whisker, I should say. The left whisker is much longer than the right whisker. So that was for Apple. And the Samsung tablets, the shape is very much skewed to the left with a longer left tail. Whisker, hello, whisker. I'm getting all my animal metaphors confused. All right. So what do we talk about? Shape, center. I don't have my data right here in front of me because I don't actually have it live on my calculator. But we would be comparing the medians as the measure of center here. But I can tell that the center for Apple, the median for Apple is higher than the median for Samsung. So the middle rating for Apple is higher than Samsung. As a Samsung user, I disagree, but whatever. Notice I didn't actually say what they were. You don't have to when you're comparing them. You just have to say which one's higher. So that's kind of nice. I like when you put more numbers in there, but that's because I'm a math person. So we had shape, we had center, variability. So let's talk about the interquartile range. So the Apple tablets have less variability than the Samsung tablets by looking at the interquartile range. And then outliers. There appear to be two outliers in the Apple data, which were, I don't know if we had this data ordered in any way. It'd be these lower ones, right? That's silly. All right. So the 76 and the 73. I'm always worried I'm looking at the wrong data. So the ratings of 76 and 73, I already forgot what they were, appear to be outliers by the 1.5 times the interquartile range rule. And there appear to be no outliers on the Samsung data. Now, I think that's very interesting, and we could have a great debate in class. Look how variable this is. Look at the range itself and also the interquartile range for the Samsung. What attributed or contributed to the ratings of being so spread out? And Apple's were so not variable and kind of tight. So is that truly because of the product? Is it because of who's measuring these? I'm still a little confused about this. They rated many tablet computers for performance and quality. Who's doing this rating? Are these customers of Consumer Reports, like readers? Are they people who work for them? I don't know. I'm going to be honest. I don't love Apple products, so I think I'm a little passionate about this for the wrong reason. All right. Learning targets. That means we're at the end. Thank goodness, because I can't read anymore. All right, guys, this is a really big lesson. We're going to do a lot of activities on this because these topics are so important to us. I really need to add a slide about comparing. I need to remind myself. We'll do that in class. All right. Promise we'll do more examples. I know that was probably clear as mud as the end, and I appreciate your help. I know you'll give it to me.